the Thursday morning session, everyone. It's a pleasure to introduce Piotr Przytycki from McGill, who is going to tell us about a pair of Garside shadows.
Thank you. Thank you for the invitation. So, Henry said it's going to be about a pair of Garside shadows. And this will be about joint work with Yika Yao. So this will be a talk about Coxeter groups. So let me remind you what is a Coxeter group. So this group will be called G. It will have a finite generating set S. And then we will require that all the generators Si are involutions. Si squared will be equal to 1. And also, if you take a pair of generators, Si and Sj, for I distinct from J, there might be or there might not be an exponent Mij such that we have the relation Si times Aj to the power Mij is equal to 1. And I will draw in a moment for you an example of a Cayley graph of this group. But first let me introduce some notions related to that Cayley graph so that I can illustrate them in one figure. So elements of a Coxeter group are called reflections if there are conjugates of the generators. So an element R of the Coxeter group is a reflection if its conjugate to some generator Si. And once you pick a reflection, you can look at its wall in the Cayley graph. So we look at the Cayley graph of this group, Coxeter group with this generating set S, and inside there we have a wall WR. So this will be called a wall. It will be a fixed point set of R whenever R is a reflection, or R a reflection. So now I think I can draw an example of the Coxeter group. So the example will be with the generating set consisting of 3 elements, S1, S2, S3, and the exponents will be the first 2 exponents M1, 2 and M2, 3 will be equal to 4, and the exponent M1, 3 will be equal to 2. So what is the Cayley graph? We start from the identity. Since these generators are involutions, identity will have only 3 neighbors, S1, S2, S3. By this relation involving M1, 3, S1 times S3 is equal to S3 times S1, so there will be a square in the Cayley graph. And the other relations have length 8, and they will correspond to octagons in the Cayley graph. So this will be S2, S1, S2, S1, S2, etc. This element will be S2, S3, and there will be another square here based at S2, because this one is S2, S1, S3, which is also equal to S2, S3, S1, and in general, this Cayley graph will tile, for this group, this Cayley graph will tile the Euclidean plane with squares and octagons. And now for the walls. So each group acts on its Cayley graph. So let's see how this action looks like here. For example, S1, when you act on the left on the vertices of the Cayley graph, exchanges identity and S1, exchanges these 2 vertices, and fixes these points. So a wall, so now I will draw the wall of S1. It fixes, these are the points of the wall, but it's inconvenient for me just to draw this infinite set of discrete points, so instead of drawing the set of points, I draw the line. But formally, a wall is just this discrete set of points. So this is wall of S1. This is the wall of S3. This will be the wall of S2. And there will be also some other walls. If you start drawing all the walls, you will get the dual tiling of the plane by these right-angled triangles. Questions? So some walls will be better than the others. These will be called elementary. So a wall WR is elementary if it is not separated from the identity vertex by another wall. So for example, if I took a horizontal wall here, it's not elementary because it's separated from the identity by this red wall. But all these red walls that I've drawn are elementary, and these are not the only ones. For example, this wall will also be elementary, cannot be separated from identity by any other wall. Same is true for this wall, and I think there is one more that's elementary, that's here. This wall also cannot be separated from identity by any other wall, even though it's a bit far from identity. It's farther than these three original ones. And it's not an accident that here you have only finitely many elementary walls. It's a theorem that Mike called the parallel wall theorem. Proved by Brink and Howlett. Saying that independent of the Coxeter group, there are only finitely many elementary walls. So 8 in this example, but maybe some larger but finite number for other Coxeter groups. So if you have finitely many walls and you cut the Cayley graph or this Euclidean plane using these walls, you get only finitely many complementary components, and these components will be called the Sch components. So we define the a Sch part is a component of the Cayley graph of the Coxeter group minus the union of all the elementary walls. So to state our first theorem, I need one more notion, the notion of the natural order on the vertices of this Cayley graph, on the elements of the Coxeter group. So we say that one element, P, is smaller or equal than another element, G, for P and G in the Coxeter group, if there is a geodesic in the Cayley graph of this group from the identity 2G passing through P. So we have identity G, and we say that P is smaller than G if there is a geodesic in the Cayley graph connecting identity 2G through P. Any questions about the definition? So the first theorem that we proved with Ika, and it was, the proof is based on a proof we earlier performed with Garside in another paper, but it was also independently found by Dyer official whole extent mark, saying that each szy component, or szy part, contains a smallest element with respect to this order. Okay, so there is a particular element in each component, in each part, that's smallest, meaning it's smaller than all the other elements in this part. So for example, it's this vertex in this part, this vertex in this part, well, in this component, it's just this one, but you see that if you take any other element in this part, there is a geodesic. From this point to the identity going through this particular smallest element. Sometimes these elements are called gates of these sets.
Are they unique?
Yes, because they are smallest. If you have two, well, this smallest one has to be smaller than the other. So it's not minimum. They are really smallest in the sense of this order. Okay.
Yeah, but then so you're saying this order is a total order? I mean,
it's not total order, but since I claim here that there is a smallest element, by definition, what it means to be smallest, it's smaller than every other. So if there were two smallest, the first would be smaller than the second would be smaller than the first, and they would be equal by the definition of the partial order. So why was it of interest to us earlier with Damian? Because we use this as a tool to prove the bioautomaticity of Cox-Square groups. So let me tell a few words about our earlier paper. So here's a definition that we made with Damian. This is the definition of the voracious projection. So this is the projection that takes as data some, say, base point G and looks for a good projection from the identity towards G. So what will it be? This voracious projection is exactly the smallest element in the szy part containing G. So for example, if this is my G, then I define this element as the voracious projection from identity towards G. And since I want to be able not only project identity towards other vertices, but any vertex toward other vertices, and I want this to be equivariant, I just defined for any part Hg the projection from H towards G. Well, if I do it equivariantly, I need to define it as H times the projection from identity towards H inverse G. So now, once I have this definition, the remark is that the distance between identity and this projection is uniformly bounded for any H and any G, just because by the parallel Wolff theorem there are finitely many finitely many szy parts, so there are finitely many of these smallest elements in the szy part, so there is a uniform bound depending only on the group between the distance from identity to this smallest element of the szy part. So by P CWT, the parallel wall theorem, the distance between H and the projection of H towards G is smaller than some constant depending only on the group. By the parallel wall theorem, the distance between H and the projection is smaller than a constant depending only on the group. Questions? So maybe I'll say a few words why this helps to prove the biautomaticity of Coxeter groups, what it means for a group to be biautomatic. I will not give a full definition, but I will draw a figure. So first of all, how does this voracious projection give rise to a good path system in the Cayley graph? So suppose you have 2 points in your Cayley graph, and you want to construct a natural path using this voracious projection. Well, then you can look at the first projection from this vertex toward that one, and then you change your starting vertex, you forget about this, you jump again, well, and eventually you arrive at your target. And now, since you want to have a path in the Cayley graph, you can just replace any of these arrows, these jumps, but by some geodesic in the Cayley graph, joining the endpoints of the arrow. This will give you a geodesic in the Cayley graph. There's a question? And since these jumps are uniformly bounded, it doesn't matter too much which white paths you take, because these green jumps are uniformly bounded. So this gives you a path system between any pairs of points in the group and in the Cayley graph. And now biautomaticity, among other axioms, tells you that if you now take a neighbor of the starting vertex and the neighbor of the target vertex, and you look at the other path defined by these voracious projections, then these paths stay some bounded number, say C prime, apart, where the C prime depends only on the group. So this is biautomaticity. And this part of biautomaticity that's called the fellow traveler property. So earlier, Brink and Holland and Mike Davies and Shapiro proved that there is another path system in Coxeter groups that satisfies only one-sided fellow traveler property. So if you assume that these target points are the same, then you have this one-sided fellow traveler property. But their path system does not satisfy this two-sided one. So I'll try to convince you today why this one is better and how it fits in the larger scheme of different good path systems on Coxeter groups. So maybe let me at least write one sentence from this discussion. The theorem that we proved with Damian is that this gives rise to a biautomatic path system for the Coxeter group. So one crucial lemma that we use, that I will write, is the following one. It's kind of a monotonicity lemma for the voracious projection. That if you have G greater or equal than G prime in our order in the Coxeter group, then the voracious projection from G towards identity is greater or equal than voracious projection from G prime towards the identity. And in fact, I want to state it in a slightly weaker form, even though it's still true without this assumption. Let's assume also here that it's greater or equal than the projection of the first element. I will draw in a moment a picture illustrating that, but once I will draw the picture, I will want to convince you that this lemma implies the fellow traveler property, at least one side. So how does this lemma imply the fellow traveler property? So I told you that one-sided fellow traveler property happens when you have the identity vertex, and then you have two neighbors. And let's assume without loss of generality that G prime is closer to identity than G. One of them has to be closer since the Cayley graph is bipartite. And now one thing that I should say maybe about this picture, about this voracious projection, the way we thought about it with Damian, is what it means to jump to the smallest element of this Xi component containing G. It means in particular that we want to jump through all the elementary walls. We want to find the best target of the jump, but our goal is to jump through all the elementary walls separating identity from G. So here, from the point of view of G, this is an elementary wall. This is closest possible to G. So this means that if we are looking for the position of the voracious projection of G towards identity, we have to jump through this wall. So in particular, the target of this jump is on a geodesic between, not only between G and identity, but also between G prime and identity. So the assumptions of the lemma are met. This projection is smaller than G prime. So we have the conclusion of the lemma saying that if we look at the position of the projection of G prime towards the identity, this element will be smaller than the projection of G. So this means that this will still be a geodesic going towards identity. And then we can iterate. When we iterate this lemma, we will project again, we find ourselves again on some geodesic towards identity, but eventually we will arrive at the identity, and you will see that both green paths fellow travel because they just follow the same white geodesic. Okay, so now I can pass to the concept from the beginning of from the title of the talk. This is the concept of a Garside shadow. This was introduced by Dyer and Holbeck. So, a finite subset, pi inside the Coxeter group, is a Garside shadow if the following three axioms are satisfied. First of all, we assume that the generating set is contained in the shadow. Second of all, the shadow is invariant under suffixes. So this means that for any element p in the shadow and some element h smaller than p for any prefix, if we look at the corresponding suffix, the corresponding suffix is h inverse p, that the suffix also belongs to the shadow. And the third axiom demands that if you have two elements, p and p prime, in the shadow, and if the join exists, let me remind you what is a join. So the join is just the smallest element larger than P and P prime. It might not exist, but if it exists, then we demand that the join of P and P prime also belongs to the shadow. And we will spend some time now trying to argue why these axioms are good, why they also allow us to define some good path system in the group. Any questions? Okay, so now for some motivation. First of all, let me motivate point 3. How this point 3 will give rise to a nice path system in the group. So let's fix for a moment a group element. So for an element G in the Coxeter group, I claim that there exists the largest element P of the shadow that's still smaller than G. Largest element P in the shadow with the property that P is smaller than G. So why is that? It's just that you can define it is the element which is just the join of all the elements in the shadow such that they are smaller than G. You see, if you take two elements, say you take two elements in the shadow smaller than G, so this means that they are bounded. And there is a property in Coxeter groups that if a pair of elements is bounded, then it has a join. So this means, and the same is true for finite collections. So if we take a finite set of elements smaller than G, then they will have a join, and by axiom 3, this join will also lie in the shadow. So this is because in a Coxeter group, a finite just a bounded, because each bounded set is finite, a bounded set has a join. And we call this element, let's have a name for this element. This will be, I will use a similar notation as for the voracious projection, but I will replace pi with p. It will be the projection of identity towards G. So the picture is like this. You have identity, you have G, and now you have some elements of the Garside shadow, say P prime, that are smaller than G. And by the definition of the shadow, actually their join, which has to exist since they are both bounded, their join still belongs to the shadow. So somewhere there is this largest element, this projection of identity towards G, and this replaces the voracious projection in this general setup. Okay, so let me write it that this allows to define analogously as for the voracious projection a path system in the group, just as before. And as before, if I want to take a projection from some element H towards G, instead of from identity, I define it equivalently as H times the projection from identity towards H inverse G. So this is what this axiom 3 tells you, that you get some system of paths. Questions? So let me elaborate a bit on axiom 2. What is it good for? So the role of axiom 2 is to prove the lemma in the top left corner. So the axiom 2 will imply the lemma. So let me convince you of that. Namely, I am supposed to check that that if G is greater or equal than G prime, greater or equal than the projection, but now projection in this general setup with the Garside shadow of G towards identity, then there is also the inequality between the projections. Okay, so let's see why does that hold. So it's just that we can look at the label. So this green path is labeled by some element from the shadow. And now, when we look at the label of some reduced path between G prime and this element, it's a suffix. So if we call this P prime, we have that P prime is a suffix of P. So P prime also belongs to the shadow. And now we are asking what's the position of the projection from G prime towards the identity. So we are looking at all elements of the shadow that brings us, such that if we draw a path from G labeled by this element of the shadow, then we land on a geodesic towards identity. And so this P prime will be a good candidate. This P prime will be an element of this set that we are discussing here. So the join of this set will be larger than P prime. So this element will be larger than P prime. So this means exactly that these will lie on a geodesic. So this is the figure justifying that since the shadow is invariant under suffixes, the lemma that we need will hold. And now the natural question to ask is, okay, but is this system of paths defined using voracious projections, is it a Garside shadow? Did we really prove this lemma with phi instead of P? So this is indeed the case, and this is another theorem we proved with Hika, which was also independently proved by Dyer, Fischel, Holberg, and Mark. That this set of voracious projections forms a Garside shadow. The theorem says that if you take set pi, which is equal to the set of all the voracious projections between identity and any element G of the Coxeter group, and this is a Garside shadow. let me at least give proof of some easier parts of this theorem. So let's first look at, for a warm-up, let's look at part 1. In part 1, I'm supposed to prove that if in my Cayley graph I take identity and then I take some element in the generating set, say S1, I'm supposed to prove that this S1 belongs to the Garside shadow. So I'm supposed to prove that this element is the minimal element in some shield part. So how could S1 not be the smallest element in this strip part? It would not be smallest if there was some element that's smaller. So it would mean that identity and S1 would have to be in the same strip part. But they cannot be because the wall separating S1 and identity is definitely elementary because it's closest possible to identity. So this means that S1 has to be smallest in its strip part because the only smaller element is in a different strip part. Okay, so this one is smallest in its strip part. If we assume already the theorem I mentioned with Diamond that there exists the smallest element, then it is the smallest element. Questions? Okay, so now let's do part 2, because this is the part that we used on the right board. We need to prove that this set is invariant under suffixes. So take an element in the, that's the smallest element in its strip part, say the projection from identity towards some element G, which is not too important. So this is one of my voracious projections, and now I need to look at a suffix. So what it means to look at a suffix, it means that I take some path from identity to this element, I take some point on this path, and then I look at this path, this suffix. And I would like to prove that this is also the label of this path is also an element, is a voracious projection now from this point towards somewhere. In fact, it would be towards G. So in order to do it, I need, like here, analyze all the possible ways to get closer from this point to this one. But if I take any wall that I meet after the first step on this yellow path, this is also a wall that I meet as the first one on the path from this point to the identity. So call this wall W. So this wall W is elementary, since this point was the voracious projection from identity towards G. So W is elementary. So this means that it's not separated from identity by any other wall. But if it's not separated from identity by any other wall, it's also not separated from this point by any other wall. So other way to say it is that if you translate the whole figure by this element H inverse W is an element. So indeed, after translating everything by H inverse, this point stays the minimal element in its strip part, and then H inverse, the original voracious projection, is smallest in its strip part. So this proves part 2. So the most difficult one is part 3. Let me just say, maybe I will not give you the whole proof. You can ask me about more details in the question period. Let me keep the axioms. But let me at least just sum one sentence about the proof of part 3. The key thing to prove part 3 is the following claim, whose proof I will skip. Namely, it's monotonicity, but in the other coordinate. So the claim is that if G prime is smaller than G, if this, then the voracious projection from identity towards G prime is smaller or equal than the projection from identity towards G. So let's see how the claim implies part 3. So it's just that if you now take two elements, P and P prime, in our candidate set for the shadow, in this set of voracious projections, then, well, P is the smallest one in its component, so P is its own voracious projection from identity to P, and similarly, P prime is its own voracious projection. And by monotonicity, they are both smaller than the projection from identity towards the join. We assume it exists in part 3. And, well, the join is larger than P, so we have, by this, we have an equality between the projections. So now we have two elements that are smaller than this. This is their upper bound. So this is also an upper bound for their join. So the join is the smallest element that's larger than these two, so it's smaller or equal than some upper bound. But by the definition of the voracious projection, this element is smaller than the join. So these elements have to be equal, and this means that this element is its own voracious projection. So everything is hidden in the proof of the claim, and maybe we can come back to it in the question period. But now I would like to say a few words about the second Garside shadow, because I promised a pair. For the moment, I've been just discussing one. Any questions so far? Okay, so what will be the second Garside shadow? So for that, I need to define what is a cone in a Coxeter group. So a cone, it will depend on two parameters. Let's say that the first one for the moment is identity, and the second is G. Is the set of elements H of the Coxeter group such that are greater than G, such that G is smaller than H. So the picture is the following. You have identity, here, G, and now you're looking at paths starting at identity, going through G, and going farther. And all the elements that lie beyond G are called elements of this cone. And now, as you can imagine, we define it equivariantly. So we define the cone of Fg as F times the cone from identity to F inverse G. And it's interesting now to compare the cones such not the first parameter is identity, but the second parameter is identity. So now we look at these purple cones that are sort of based at identity, and we ask what are the elements here, F, that give rise to this cone? Maybe there are more elements, say F and F prime, that give rise to the same cone. So we consider them equivalent. So we decompose the whole group G into cone parts. So earlier we decomposed in shape parts, now we decompose it into cone parts, where the vertices F, F prime belong, that F and F prime belong to the same part if the cones are the same. If the cone F identity is equal to the cone F prime identity. And it's an exercise that these cone parts have reasonable geometry. First of all, they are convex. So remark, cone type parts are convex, and moreover, each cone part is obtained by putting together several shape parts. So the partition into shape parts is a refinement of the partition into cone type parts, and are unions of shape parts. So it's a decomposition, again, infinitely many parts, but which has smaller number of parts than shape parts. So in some sense it's better. And there are analogies between this shape partition and cone type partition. So the first theorem I want to mention is the theorem proved by Ika in his PhD, that each cone type part contains a smallest element. So this means there is a chance of defining a good path system again. And in fact, okay, so this is the theorem that we proved together. If you look at the set consisting of all the smallest elements of cone type parts, they form a Garside shadow. So the axioms are satisfied, which means at least you know already today that there is a nice path system and it satisfies one-sided fellow traveler property. And a recent development by my student, Fabricio dos Santos, is that this Garside shadow, and in fact each Garside shadow gives rise to a biautomatic path system. So in some sense, this path system using the cone type partition looks to be more efficient because the Garside shadow is smaller. It still gives rise to the bioautomatic structure. And in fact, you have many of these Garside shadows. Any finite subset of the Coxeter group sits inside some Garside shadow. So if you want to prove some things about Coxeter groups, you have plenty of choices to choose your path system with which you can manipulate the group. So thank you for your attention.
Questions for Piotr?
So, like, everything you talked about here was in the world of Coxeter groups, but it seems that, for instance, for like if a group with like a wall space structure on its Cayley graph, and if you assume that you have like a parallel wall theorem and like gated half spaces, are we able to define similarly these sort of shadows and obtain arithmeticity? Because, like, for instance, for cat-zero cube complexes, you have something similar, and it looks like you recover like the cube path of Nebel Reef, right?
So the most difficult part of the proof is hidden in the proof of the claim, where for the moment both us with Damian and Fabrizio use the reflections. But we now have also, and also they use something, we use something that's called bipodality, introduced by Diane Holbeck. So it depends whether these other groups would satisfy this. Either they would have reflections, or at least they would have some weak form of this bipodality. So there are some things that somehow I didn't show you yet, but we don't have good groups that fit in the same scheme. For the moment, we have just Coxeter groups, but we have more bioautomatic systems than at the beginning.
How hard is the proof of the parallel wall theorem these days? You have to use Brink and Hallett still, or?
It's still hard. The hardest, so I tried, one of my students was working on simplifying the proof, and it seems like for the moment the hardest thing is the proof that you have a uniform bound on the set of pairwise intersecting walls. With root systems, it's just one paragraph, that there is a uniform bound on the size of the pairwise intersecting walls given a Coxeter group, but we cannot do it geometrically. You cannot do it without roots. If somebody has a good idea how to do it, then I will offer some reward.
So does knowing that your voracious path system is a special case of this Garside shadow tell you something new about the path system, or is the takeaway here that you ought to be thinking about other Garside shadow path systems?
It simplifies some parts. So, for example, this statement that there's a uniform bound on the distance between the vertex and its projection. The paper with Damian, we have a one-page proof using cat-zero geometry. But once you realize this viewpoint Garside shadow, I showed you, it's immediate. So, but I think the main hope is that maybe you will be able to do more things using this cone-type partition path system.
Let's thank Piotr again.